Okay, thanks, Stephen. Um, so this presentation was a sort of a last-minute thing. Um, Believe it or not, I prepared this only today in the morning, and so some of uh, some of this stuff is um, it's a bit rusty, I suppose. No, you wouldn't call it rusty. I'm not sure this presentation is going to be smooth exactly. Um, but it's a topic that I think is interesting to me and is probably interesting to a lot of us, given that probably many of us use these models. As to whether I'm an LLM or not, I hope not, but questioning the nature of my existence isn't something that I really want to do in the Netherlands while I'm alone. Um, this presentation is also designed in Figma. I was originally designing presentations in PowerPoint. I decided to use Figma for the first time, which has been an interesting experience. The formatting might be a bit weird as far as the slides are concerned. Many of you would have probably interacted with LLMs like GPT and Palm and DeepSeek, etc. I work as a PhD candidate in the Netherlands. I'm currently working in a hospital, and much of my work actually involves computer vision, which is interesting because I'm talking about language models in this presentation, which is primarily natural language processing, but I'll explain why it's an important part of my work anyway. I don't really come from an AI background. My first project, I did that during my undergraduate studies in mechanical engineering as part of a small research attachment. And that was also in computer vision. It was in AI-driven, sort of digital pathology. Pathology is sort of like medical microscopy. It's when a clinician, a doctor, essentially extracts a piece of tissue, which could be cancer tissue or something, from patient's, deceased sort of tissue, which could be a tumor tissue, it could be some sort of lesion, scar tissue, whatsoever. And then they put it under a microscope, they stain it with some liquid and they give it a certain color and they try and see what are the features in that tissue. So I was sort of developing models to detect anomalies on that tissue, diseases, essentially. Sometime after that, I worked as an AI engineer in Singapore. I was developing models for things like 3D computer vision. I was also developing models for natural language processing. So one of those problems was, the building of a dental diagnosis assistant. So what it would do is the dentist identifies observations, in the tooth the teeth as they're doing an examination. You take that text diagnosis and then you pass it to a model. Then we wanted to see whether or not the model could return a possible diagnosis for those observations by examining dental literature. So that was actually one of the first times I interacted, with an LLM in the professional context in my work. And so during this period of time, I have to say that I didn't really like LLMs when they came up. For me personally, I was very much interested specifically in computer vision models. And I felt like LLMs were being forced down our throat. My bosses, they thought that LLMs were the next big thing. They were like, these things are going to be part of the future. They wanted us to come up with LLM training material. They wanted us to document our use of LLMs in our projects. Like if you were using ChatGPT to get advice on like coding problems and things like that, they wanted us to document our experience so that they could find out what are better solutions for us to work with LLMs. They were also looking for more LLM related projects. These projects involve things like grading the reports that students submit for their assignments in school. Things like grammar checkers, things like LLM related, like sort of healthcare projects and stuff like that. And they were rather complex. They were rather, irritating. Part of the reason is when you're working with an LLM, if you're not deploying an LLM locally, you're basically using an online service like a GPT through an API or some sort of code, things like that. But essentially what happens is every time you query the LLM, every time you make an LLM call by typing something out and passing it to the LLM, you essentially pay a certain amount of money. And we had to monitor those costs whenever we did our projects as well, which was really annoying. But at last, all things considered, I find myself using these LLMs for one of the problems in my PhD project as well. So I haven't actually managed to get away from these things. In fact, these things have become a part of my work. And I thought it would be a good idea to share what are some of the developments in my field that have sort of been revolutionized, if I said that right, by an LLM. So LLM sort of popped up around 2018. But natural language processing models, or NLP models, have existed for quite a long time, prior to the existence of LLMs. Before 2017, language processing was very much a sequential data problem. It still is. But it was often handled by these recurrent neural networks. And these networks sort of process words in a sentence as like tokens. It assigned numbers to these words, based on their lexical meaning, based on what sort of positions they were in a dictionary, things like that. But the problem with many of these networks is that it couldn't really remember information. Capturing contextual information for these models was very difficult. When I say contextual information, I mean for a certain paragraph, what does this word actually mean? And capturing those relationships between words as well to identify information that was important was also quite difficult for these models. As they went through bodies of text, through paragraphs and stuff, they used to forget information as well. So storing that information and remembering things in order to have a conversation and stuff was really quite difficult for these models. But then sometime in 2017, some researchers from Google, they introduced the attention mechanism and the transformer architecture. And these new models could actually capture the relationship between words in different contexts. And they could even capture portions of data that were the most important in relation to the tasks that they were doing. This transformer architecture, wasn't just something that was applied to text, it was also applied to images. We had the vision transformer architecture that came out soon after. That's a different story, of course. But this, inception of this idea, this mechanism in 2017, is what led to the development of large language models. They form, if you think about GPT, generated pre-trained transformer. Transformer stands at the core of what GPT is capable of doing. So when large language models came up, these were huge models that were trained on a multitude of data sources, with a large number of parameters, and they were capable of things like, text generation. But the question is, how do you train a large language model? And to me, that's actually a very interesting task. For any transformer model to be effective, whether it's a text transformer or a vision transformer, I won't talk too much about the specifications of the architecture itself because I think that will confuse a lot of us. But the idea is, in order to train these models, you actually need a large body of text sources. And so these text sources can be obtained, through crawling through text. If it's medical data, it could be a large number of medical literature, whether it's from research papers or whether it's from textbooks. But these resources are sort of consolidated. Some of them are open source, some of them are not, and they are extracted and they're used to train a model. How does that training work? There are two different methods. One method, of course, if you're training a generative model, is to make it perform next word prediction. So you have a certain body of text. What you do is you mask some of the text at the end, and then you get the model to predict what is the next word based on the previous words. Of course, the model is going to make mistakes at the start, but that's the whole idea. It starts to make a guess, and that guess is updated based on what it got wrong, whether it got it right, how close was the answer. Masked language modeling is another method of training models, which is instead of masking the end of the text, instead of leaving that part blank to predict the next body of text, you mask part of the middle of the text. These models that are trained on this sort of like mask language modeling, it's actually, these models are called bidirectional encoder models. And I think there's a bit of variability in whether or not people believe these models are large language models or not. A model like BERT, which is a transformer-based model, it is a large model, it's a language model, but it's not capable of generating text the same way that GPT is capable of generating text. So sometimes, when we look at research papers for language models, there's a bit of discrepancy in how people call, in what people call a large language model. A model like BERT that's not capable of generative language modeling, which means generating text, which is the stuff that ChatGPT is capable of doing, may not be termed a large language model. In contrast, GPT may be called a generative language model in some bodies of text, because people want to differentiate what they believe is a large language model and a large language model that is capable of text generation. So be wary of these terms, if you decide to read articles or you read, research papers and stuff, because there is some difference in the way these models are termed. But anyway, what's going to happen in the midst of those predicted tasks is the LLM will end up making mistakes. It will make a guess with regards to the words that are missing, the words that are masked, but it will keep making those mistakes, and it will keep updating itself, its weights, based on the ground truth information. So the LLM, it starts to learn what's correct, what are the patterns that will help it achieve a correct answer as far as like the blanks and all that are concerned. As it keeps trying to update itself to fill in those blanks correctly, as its accuracy improves, it eventually starts to learn a number of patterns with regards to the data. So what are the words that appear together? What are their contextual relationships? You can see a very nice example of that on the left. So for example, like man, woman, a king and a queen, what are those relationships, in terms of the gender, in terms of the context, what are those positions, for example. All these things can be represented as numerical data, and the closer the numerical representations are to each other, the likelihood is that the words have a very good contextual, very close contextual relationship. You can also learn the rules of grammar and structure. These are key, of course, to things like language generation. And with the more recent models, it's even possible that you have reasoning capabilities. I don't know whether many of you are actually, attention is actually the mechanism that helps helps the LLM learn those relationships. For any of you that's actually paying for the GPT subscription, the ChatGPT subscription, if you are paying for the Plus version, you would have seen that they've actually introduced the newer reasoning capability induced models. So the O1 model and I think the O2 model, these are now available to people who are paying for that subscription. These are actually capable of reasoning capabilities. It takes them a while to make the predictions, but they are capable of, understanding things like, for example, a fever and a cough. It likely means that there is a respiratory issue with that patient. So to be able to make those decisions about data, about the relationships in data, those are some of the advancements that we've seen with the newer generation LLM models. With that, I think that I can probably talk a little bit about digital medicine. So I think it's very important for me to delineate this concept of digitalization, because I think it's something that we don't take seriously enough. In healthcare, much of the information in the past used to be presented in a form that you could only visualize like yourself. Text used to be written. If you were talking about microscope slides, they were pretty much in slide format. You needed a microscope to view them. If you were talking about an X-ray was basically printed on this special piece of paper, on this special film. So it was very hard to work with that data. And then eventually people started introducing things like optical character recognition that could, work with written text data and then digitalize it, put it into sentences. Doctors are presently using computers to record their information and diagnosis. Slides, as far as microscope slides are concerned, we now have special scanners in hospital to scan that and put it in computers in the digital realm. And because of that, we've been able to develop models that are tailored towards healthcare tasks. So LLMs basically work primarily with text data, although, if you're talking about things like audio data, it's also possible to now develop, or run models that are capable of translating that data to text data as well. And so we've allowed LLMs to interact with that data by virtue of that. There are a couple of tasks in healthcare that LLMs are capable of working on. Text summarization is one very good example of that. So if you're talking about the clinical records, from patients and all that, these are very extremely sort of complex information. And some of it is not really important towards making a diagnosis. If somebody is having a conversation with a patient, not all of that conversation is probably relevant to a certain diagnosis. And that's part of the reason, that's part of the usefulness of the attention mechanism. It's capable of paying, important attention to the important parts of the conversation that are key to a diagnosis. And it's capable of extracting that information. Interestingly, the example that I've presented here is sort of the opposite of what I just described. So what you would expect is an LLM would listen to a conversation that goes on between a doctor and a patient. It would sort of read what's taken from that conversation, the notes from those conversations, and it would then try and generate a summary that you would then want to analyze and you could then interpret. But this is the opposite. These researchers actually created a sort of synthetic conversation using an LLM from the clinical notes. So what the LLM does is it reads the clinical notes that are recorded probably by a clinician or something like that, and it tries to generate a synthetic conversation that may have gone on with the patient and the doctor. And I thought that was pretty interesting, doing it the opposite way, because you would normally want the summary, but this is the conversation. And likewise, LLMs are also capable of conversing with patients. So, whether or not it's their memory capabilities or their sort of reasoning capabilities, I have to say reasoning with open inverted commas now, thanks to Roy's comment earlier. Through these capabilities, they can actually learn to ask sort of relevant questions to the patient. So in this case, the patient said that they have a rash with blisters and all that stuff. The LLM deemed that it was important to ask, the patient first off for their age and to get sort of their demographic information, things like their sex and stuff. And then it was able to go back to the conversation and ask, how long have you had this rash, and things like that. We don't really know how effective this is because there are studies that are going on to check whether or not patients are actually happy talking to these kind of models, happier talking to these kind of models. But I mean, the nice thing about an LLM is its capability to be sort of patient. For those of you interacting with ChatGPT and stuff, I suppose you would see that it exhibits a sort of it doesn't really have problems like anger management issues and stuff like that. So it's capable of being reasonable to a certain extent. But yeah, people do, in the clinical setting, what we're trying to do is, because the manpower that's capable of, talking to patients and stuff like that is somewhat limited. In order to have, to ensure that patients have a human-like conversation with someone, to feel like they're talking to someone that cares about their conditions and things like that, we introduce LLMs. And these things are thereafter capable of presenting a summary of those clinical records to a clinician. And they might even be able to present a sort of diagnosis at the end. One of those things that when I talked about LLM models sort of generating synthetic data, it sort of reminded me, in the past of these generated adversarial networks. A while back in the science circle, I think about maybe about 4 years ago, I talked about generative AI in the computer vision context, and it basically involved like two models competing against each other. One model exists to determine whether or not a generated image is fake or real. One model is capable of ascertaining whether or not that information is capable of transforming noise information and things like that to generate fake data. So these two models are sort of playing a game with each other. One model is trying to determine whether the other model's generated images are fake. It wants to make sure it can determine delineate the fake ones from the real ones. And the other model is basically trying to trick this discriminative model, and they're both simultaneously training at the same time. But these days, you can have models that are working collaboratively, and a large language model is particularly capable of integrating data from multiple models and aggregating their data together to present more holistic information or a holistic diagnosis. So, for example, the imaging data that is captured for the patient, the text data that the LLM obtained earlier in the conversation with the patient or from the doctor's notes, reports with regards to like the genetic markup of a patient's tumor, for example. These sources of information, they can be processed by different models, whether it's a transformer-based model or a convolutional neural network or an autoencoder, different neural networks, to process that information and to give outputs that can then be processed by a much larger model like an LLM, which is capable of aggregating that information and presenting a summarized diagnosis. From here, it's also possible for someone to interact with that data, to ask it questions. So to ask the LLM questions about what are the key factors in making a certain diagnosis. What is the definition of this sort of condition? What are the other parameters I should be looking into? For example, if the LLM suspects a particular diagnosis, I may have done an analysis for a certain set of genes, but there might be certain genes that are important towards the prediction of diagnosis, certain mutations that are important towards the prediction of a diagnosis that I may not have tested for. So a doctor can look at that, and they can basically order more tests based on the missing information. And that advice can actually be presented by an LLM. And I think that's one of the use cases that I'm probably more interested in. LLMs as a form of diagnostic support to clinicians. These are the things that you may have missed out. These are the things that you can look at. Rather than LLMs providing a diagnosis, upfront and telling the clinician it's probably this, because that sort of removes the capability of the clinician to be intuitive about their diagnosis in the first place. So I rather, these models function as a sort of diagnostic aid, and I think That's what most of us researchers in the healthcare community work work towards. And with that, this is sort of my interest in LLMs at this point. So I work with medical images. My job is to sort of develop models that are capable of diagnosing images based on certain ground truths. So, for example, based on the tumors, the mutations and all that stuff, I want to see if a model is capable of predicting those mutations based on the images that are presented, the images of the tumor itself. The problem is much of that data that I need, the ground truth information with regards to a tumor and stuff, is presented to me in this format. This is a free text pathology report, and it's often the way pathologists write reports for tumors. The problem with this is much of this information is not structured. The key information that I need is not exactly presented in a nice table, so that I can work with it a lot more easily. But I can use a large language model to extract that information and structure it in a nice format so that I can use it for my downstream tasks. Like I can say that, for this image, it's definitively this diagnosis or this gene is mutated or not, things like that. So one of the tasks that I'm exploring, and one of the tasks that's actually a popular research subject in literature, is this medical report extraction using a large language model. How do we make this work? Obviously, you have the LLM, but the key to making sure the LLM is capable of doing these tasks to a certain degree of accuracy lies in prompt engineering. And prompt engineering was a really big thing when LLMs sort of were introduced. People, I think, thought that prompt engineering was actually going to be a career instead of being a traditional programmer. Prompting is about the instructions that you pass to an LLM. It's basically a set of text-based commands. And often when we talk about prompts, we think about whether or not we're explaining the task to a human well. Because nowadays, LLMs with their level of understanding and their level of reasoning capability, reasoning with the inverted commas capabilities, these models work really well when you are capable of making your instructions very specific. And to that end, one way is to tailor the prompts to make them very clear. The other way is to provide examples in this prompt. And so to that end, there are these things called one-shot and few-shot prompts. Now, one-shot and few-shot learning isn't an idea that's exactly new. For very large models that were trained on a lot of image data, for example, this concept of providing like a few examples with relation to the task that you wanted to use the model for to improve the model's capability, that was a thing that was introduced a while back. With regards to the LLM, you could basically include these examples in the instructions to see whether or not it improves the models. And often, at times it's the case that you don't really have a lot of space to provide a lot of examples to the models to make sure it does well. So what would you do then? You have a certain prompt, there is a certain length for which you can design a prompt. There are a certain number of words that you can use, so you can only provide a few amount of examples. What can you do to improve the model's capability to do well in the task, to be specific about the tasks that you have assigned it? And one of those ways is fine-tuning. Fine-tuning is not a new concept, of course. It's something that's been introduced for a very long time. In computer vision tasks, for example, and I presented this a while back at the Science Circle, if you have a model that's trained on a large amount of natural images, say, birds and or insects, buildings and cars, things that you can get off the internet quite easily, millions of images, you could train a very, very large model. This model may not have seen medical images yet, but you can retrain that model by having it look at medical images specific to your task. Maybe these are histopathology images in this case. So you can then thereafter sort of try to fine-tune the model using those set of images. You don't need a very large data set, and it will be still capable of performing very well at the task. With the LLMs, it works the same way. You basically provided a number of examples. So you say, okay, this is the example text that I have. Maybe I want the LLM to be capable of summarizing that information, or maybe I want the LLM to be capable of translating that information. I'll provide the ground truth. I'll provide the ideal answer that I want, and I'll pass a couple of examples like that to the LLM. Now, if I take a very large model like GPT, the model behind ChatGPT, if I take that model, it has a very generic understanding of a large amount of information from a lot of data, which is not necessarily specific to medicine. But by providing it those examples in medicine that are key to my task, that are specific to my task, I can fine-tune the model because it already has an understanding of things like the grammatical structure or the relationship between certain words. I can fine-tune that model to perform specifically well with regards to my task. The importance of this might elude you, but in medicine particularly, this is really important because there are certain problems with models that are trained very well generically in a large amount of data sets. For example, their capabilities to work ethically might be somewhat limited. So for example, in this case, you have a LLM model and a clinician is asking it whether or not it's possible for them to manipulate test results to cover up a medical error. And it's asking the LLM how to do that. A model that may, is not necessarily fine-tuned and sometimes used in a medical context, if it's not properly trained, it may not have these ethical safeguards. And it may answer that question in order to, because LLMs, I think they're rather people pleasers usually. It may give an output regardless of whether or not that output is somewhat ethical or not. But if you fine-tune a model and you specifically told it in some of your examples, you showed it examples of how a person can try to be unethical with an LLM, how they may ask it to do things like, tell me how to manipulate things and stuff like that. You can train the LLM model to output, to give an answer, even if it knows in its large database, how to manipulate data and things like that. You can tell it to say that it's not a good idea to do that. I will not give you an output. So these are one of the ways that we can improve the safety of those models in LLMs. With that, I should probably also talk about some of the dangers that are involved in the use of LLMs. Hallucination is one of those problems. I don't think you see this as much with the newer generation of GPT models, but for those of you who had access to the cheap 3.5 GPT model with ChatGPT, the older generation of models, you would have realized that if you had a very long conversation with ChatGPT and you kept, talking to it, there is a possibility that at some point those outputs that the model releases are very erratic. It's not well thought out. Sometimes the information is false. Sometimes you can even convince an LLM that it's wrong and give it information that is not factual. So if you keep telling the LLM, for example, Charles Lindbergh, 1951, he was the lunar pioneer, which is not the case. If you had kept telling the model, Neil Armstrong is not actually the person who walked on the moon. If you had kept prompting the LLM that way, giving it this information, there's a possibility with the older generation of models that the LLM would have actually processed it and said, okay, yeah, that's the right answer. And that form of hallucination and stuff was actually quite a big problem, and it still is a big problem to an extent. One of the things that we also see with LLM models is they do have the right amount of information, the correct information based on their training and stuff. But that information also makes them hallucinate based on the information that was provided. This is an example of a source attribution error. In this case, I have asked the LLM to summarize information from a free text pathology report. The diagnosis in this case is a glioblastoma, and the LLM is asked to extract information from the report. Now, it is the case with the new diagnosis of glioblastomas with the based on the WHO guidelines, the World Health Organization guidelines, that an IDH mutant tumor, a brain tumor, an IDH mutant brain tumor, is not a glioblastoma. So what happens, is with an LLM, it would recognize that the IDH, glioblastomas that are diagnosed are generally IDH negative. They are negative for that mutation. This is true. This is true if the primary diagnosis is a glioblastoma, but it's not the case in the report. You see that the clinician in this case has not done, immunohistochemistry to extract that ground truth for the IDH mutation. So the LLM is correct in some sense in saying that there should be a negative IDH mutation in the case of a glioblastoma, but it is wrong in representing that as something that it extracted from the report. And so that can be quite scary. And how do we deal with that? Well, we need to be very specific about the prompt that we pass to the LLM. And we often have to introduce things like honesty and stuff as a part of the prompts that we present. For example, with this prompt, if we just told the LLM to summarize the diagnosis and the relevant prognostic markers, it might run into those errors in which it starts hallucinating that this information was present based on the diagnosis and stuff, based on the information that it was trained on. But if we tell the LLM, if we are specific about telling the LLM that we only want the information from the report, then it's highly likely that the LLM will not hallucinate. Fine-tuning will probably improve this as well. So in that sense, this is one of the reasons why prompt engineering is really important. Being very specific about the instructions that you pass to an LLM is important. And it's also one of the reasons why I feel that, LLMs can actually be a good educational tool in some sense. I know that people are a bit worried about, how it's going to result in our, the lack of our ability to think and things like that. But I think that one benefit of LLM, the use of an LLM, is it teaches us to be very specific about the instructions that we pass to it. We have to be very clear in the instructions that we want if we want to get the output, an output that is of high quality, that addresses our needs and so on and so forth. So in that sense, I think there are certain things that we can learn and improve on if we learn to communicate with these models. Another very big thing about using LLMs is that I have one more slide here, but it's missing. But when we're talking about medical-based LLMs, using ChatGPT is a no-no. So one of the things that people in hospitals are really worried about is that clinicians or even students per se are going to take information wholesale from pathology reports and pass it to ChatGPT, which is online. So one of those things that people are worried about is that the clinical identifiers for a patient, like the patient ID, the demographics and things like that, will be passed to an online LLM because people assume that it's secure and things like that. So that's quite a big problem. So in that sense, when it comes to medical data, we can't work online. We have to download these models to our local computers. They're very large models, so you need the computational power to work with them. And they need to exist locally on our servers in our environments. So there are certain policies. In Singapore, you have the Personal Data Protection Act, things like that safeguard patients in those circumstances. But how do we train those models then? If you want large amounts of data to train those models, especially if the data comes from different hospitals. It's hard for you to work with that if hospitals have to pass that data to somebody else. Hospitals are often very reluctant to do that. Um, but there is a new advancement in machine learning. It's called federated learning. It's where you can have multiple local models that are trained on a local hospital data. The information from that model mathematically can be passed to update a global model that exists somewhere else, maybe in one of those hospitals or maybe in a lab somewhere else or something. But the idea is based on those local updates that are being used to update the global model. You're not actually passing the patient information. You're not passing any of that information. You are passing the mathematical updates that actually happen to the model to increase its data set, the local model. And federated learning is one of those advancements that is being explored in not just with large language models, but with computer vision models and all that stuff as well. In order to work with data from different hospitals, it's usually the case that if you have different information from different hospitals, your model is capable of generalizing better because there's a lot of variation in the way doctors from different hospitals may write their reports. There's a lot of variation in the scanners, the MRI scanners or the image scanners that may be present at different hospitals. Those variations are things that we like when we develop models because those allow the improvement of the generalization of those models, the strength of those models. So to conclude, I think that, with large language models in the medical context, you are presented with a large variety of challenges. It's a very sensitive field. A medical diagnosis has a lot of implications with regards to a patient's quality of life, their survival. So it's not a joke when we use any AI model in the medical context. And those challenges, I think, allow for improvements of AI models generically. I think that introducing those safeguards, it would probably be applicable in a number of contexts beyond the medical field. It's just that the sensitivity of using those models in the medical field is generically a lot higher. And I think that, those challenges are quite exciting. And I hope that you use some of this stuff in this presentation to probably look up those things in online and see what those advancements are. I think there are a lot more advancements in the medical field. The use of multimodal data, for example, is one other challenge. The generation of fake image data and the way that people are dealing with that is also a challenge. The copywriting of data is also a very interesting challenge because a lot of these LLM models are trained on data that is scraped. So how much of that data can then be reproduced? Can you write me, will the LLM be able to replicate, the writing style of a certain author, for example? And then what happens then? You'll be basically copying information and stuff and copying the style and stuff, and that's not exactly what people want to happen. So how do people manipulate data so that people who are scraping data will train models that are bogus, not capable of doing that? That's also an interesting challenge. And that's all for me. I hope you enjoyed this presentation.
Hey Jude, that was a great talk. Roy just put a question in the local chat. Can you address that and maybe some of his other prior chat comments?
Yeah, I'm thinking about that. There's actually a metric in evaluating models called top K. Top K is when you use the sort of top 5 predictions and see whether or not the actual answer that you want, is a part of those predictions. So, for example, you could have 3 predictions, 3 possible answers that you want. And then out of the top 5 answers, maybe you want to see whether or not those top 3 answers are present. And those top 3 answers will then be presented, top 5 answers are presented. If it turns out that, based on the top 5, you're getting the top 3 responses as part of them, or maybe you have to increase it to top 10 to see whether or not those answers are there. I do think you probably want to reduce the number of responses that you present to the clinician so that they are specific, based on like a certain probability and stuff. But yeah, it is usually the case that with any model, not just an LLM, you want to pick the top few responses to show that probability as a sort of diagnostic support to the clinician. But ultimately, it's the clinician that sort of makes a decision about whether or not the response is valid or not at this stage, at this moment in time.
Yeah. One of the major challenges that, and this was mentioned in local chat by Tagline as well, that, you know, we base a diagnosis in many cases starting from a point of the patient describing things that are going on with them that are wrong, and or at least unusual, or that they note in their own mind. And so in most cases, I have to imagine AI models are trained on diagnoses where, if you look at the medical literature, you say this problem, this pathology has this symptom. But I wonder if it'd be possible to train an AI that was based on a whole bunch of patients' responses, in which are incomplete, messy information. And in some cases, do you think you could train those to actually be better at dealing with what is the lack, the misinformation that could actually help doctors in comparing to the medical literature, maybe help some patients where, again, it could identify cases where people say these symptoms, but it's not a complete picture for that individual doctor, but it can give insight where there's a subtle pattern AIs could recognize independent of it being true.
Yeah, I talked previously about the notion of AI models that are capable of suggesting additional tests that are required, that are missing for a specific like diagnosis. In this case, of course, that you know, going back to Roy's case, you couldn't establish a single diagnosis. You would probably have to look at multiple diagnoses for the same like set of symptoms. But maybe the patient has provided them, and you know, there's something that's incomplete. Based on, you would probably have to go back from a possible diagnosis. The LLM model will probably be able to suggest tests or additional questions that should be asked. In fact, I think the current models are capable of doing that. Even the generic models like ChatGPT, you know, you tell it you have a certain set of symptoms, and then you tell it, okay, I'm worried that I have this. It will probably be able to tell you that, oh no, maybe you still have to check for this, you have to check for that, you have to do this, you have to do that. And I think it's capable of probably asking additional questions about your diagnosis that, you know, were probably based on the incomplete information that a patient provided. So it's capable of doing that, but I think to make sure that it doesn't really fly off the leash in suggesting a diagnosis and stuff, if you want to be even more careful and make sure that it's releasing things like possible diagnosis and then additional tests that it needs to perform, you probably want to fine-tune the model. So there are models like PubMed GPT and Biomed GPT and things like that are specifically trained on a specifically fine-tuned from, on large bodies of text data and stuff that are capable of that. I would say that if the model that you currently have is not capable of doing that very well, you probably want to fine-tune it.
Jude, I actually prompt you on something that was written that Tagline said, because I find this interesting too. We have a lot of specialization within the medical field. And so obviously, if you can get correctly diagnosed for the right specialty, then that is the best person to talk to. But there's also this difficulty of getting correctly diagnosed because lots of symptoms can be indicative of different bodily systems that you have different specialists for. So do you have any insights where AI might be able to help with that?
Ooh. So that ties into the problem of generalization and stuff. One of the things is like whenever we train an AI model, it's usually in a single context, a single field, because you only have data for that much. Curated for that specialization. for example, soft tissue tumors and stuff. So maybe a certain diagnosis in a soft tissue tumor, a certain set of symptoms and stuff might also be indicative of another disease like a brain tumor. In that circumstance, you would have to make sure that the model is generalized well across a number of fields. And I think it's something that people, have I think that's probably a challenge that people are working towards, like the generalization of models across different specialization. One interesting development in this area is this thing called meta learning. So meta learning is when you have a single model that's capable of working with multiple models for different specializations, whether or not it's working across different data modalities or working across different data categories and stuff. In that circumstance, it might be possible that you have multiple models that are trained specifically on different specializations themselves, and you have a single general model that's capable of calling on these models for a single, for a received diagnosis and stuff. So maybe one model functions as a general practitioner, and that model sort of suggests a certain specialist model in order for it to get a more specific diagnosis and stuff. But of course, the computational power that's required to train all those models simultaneously, perhaps, or even train those models individually and then operate them simultaneously it's quite large. I don't know if it's present. So that's probably it's something that people are working towards, but it's not something that people have explicitly. I don't know that people have explicitly developed a reliable model that can be FDA certified for that sort of diagnostic strength.
Cool. That sounds like a good answer to me. We'll see what happens. I do want to call back to one more thing in local chat. That was an interesting point, which is that Roy brought up, should we call what AIs do using the term reason or reasoning? Do you think that is a fair term to use?
It's likely not reasoning. I mean, you would like to say that it's like, reasoning. It is ultimately a set of mathematical correlations that the AI model is making. Just that, it's learning certain statistical relationships based on what's documented about human reasoning that therefore allows it to perform that. So we can't call anything that the AI is performing, decision making or reasoning or things like that. It's basically what it is explicitly doing is actually making a statistical sort of prediction, based on things that it has learned. But the closer it gets to doing it, to a human's capability of doing that, by making those predictions, the more I suppose people have deemed it appropriate to say that it is somewhat capable of reasoning and stuff. So I suppose it depends on which angle you approach it from.